So this is going to be, I don't know, like an overview of a little bit of different aspects of EPR with some fundamentals and some examples. I will skip through some parts because I noticed like last time I gave this, I spent a lot of time with some things that were not really like important. So, well, you all know probably that magnetic resonance is about inducing transitions between spin energy levels, which are separated their energies when you apply a magnetic field. So that can be nuclear spins or electron spins. So the magnetic moment of an electron is this mu vector, which is proportional to its spin. And this is the gyromagnetic ratio, and this is a value called G value that for a free electron has a value of 2.0023, but for an electron in a molecule can differ from that value. So classically, the energy of a spin on a magnetic field is given by the scalar product of its magnetic moment times the external magnetic field vector. So a scalar product between two vectors gives a scalar, which is just a number, the energy. There's a minus sign. So basically that's the classical interaction between a magnet and a magnetic field. So because of the magnetic field is written like this, you can move the constants outside and you get like the quantum mechanical version is a Hamiltonian, which all this stuff are basically numbers, although this is a vector, but it's a vector of numbers. And then you have the spin operator. So a spin operator acts on the spin variables of an electron or a set of electrons and produces their basically their eigenvalues and eigenvectors. So basically the different spin states each have a spin value. Ms equals plus minus 1/2, for example. That's for a single electron. So you can calculate the energy levels that depend on the Ms value. So far so good. So that's all, I think, basic, it's covering most, physical chemistry, spectroscopy stuff. So when you sweep in an EPR experiment, you usually work at a fixed frequency. So I'm going to talk about that later. And you sweep the magnetic field. And when the frequency times h is the Planck's constant matches the difference in energy between the two levels, you can induce a transition by absorption of that electromagnetic radiation. So the resonance frequency is given by this delta E that corresponds to basically the difference in energy between the two spin levels. So plus 1/2 and minus 1/2, the subtraction of those numbers gives 1. So you get like the energy is the Bohr magneton times G times the external magnetic field. Okay, so you can calculate the G value, which is more or less related to, well, it's related to the position of the resonance with this formula. It depends on the frequency and inversely on the magnetic field. Okay? So these are all different units and numbers for the different constants that appear, and you can use this formula if you use the frequency in gigahertz and the magnetic field in millitesla to calculate G value. So this is already done by the programs, like you just pick the G scale and it will do this transformation. But this is an inverse scale. So larger fields in that direction mean lower G values. So how do we calculate the properties of a spin system? What we use is a spin Hamiltonian. So the Hamiltonian, as we talked about yesterday, is the operator, gives the energy of a system. So the electronic Hamiltonian contains different terms: kinetic energy, electron-nuclear, electron-electron repulsion. But well, it gives, depending on the system, if you have an atom, it will give you different states of the different orbitals of that atom. There used to be a hydrogenic atom, and then those will have different energies. If you have a more complicated system, like an ion in a ligand field, you have more orbitals, more states, but if you only consider the ones in the third row, for example, for, I don't know, iron, cobalt, copper, etc., you have 3s, 3p, 3d. These are the generated for the free ion. When you put a octahedral ligand field, you get a splitting, for example, of the d electrons. Everybody knows this. Then you have a further splitting when you have an axial elongation, and this other case, like you have a more extreme splitting when you have a square planar case. So that all is caused by the different ways of writing an electronic Hamiltonian. So in EPR, what we are interested in is spin properties. So we don't use the full Hamiltonian, which would be used in a DFT calculation or another type of calculation, but we use a simpler Hamiltonian, which is called the spin Hamiltonian. So the spin Hamiltonian only depends on spin variables. Spin operators can be electron or nuclear or both, but it doesn't act on the whole spectrum of the electronic Hamiltonian. It only acts on the sublevels, the spin sublevels. So it doesn't change, or it doesn't change much the electronic energies, but it allows us to describe the splittings only due to spin interactions or spin interactions with an external magnetic field. So the spin Hamiltonian is like much smaller and much simpler than the full Hamiltonian. And we take the spin Hamiltonian and we have different possible states of the total spin and its projections, and this allows us to build an energy matrix that can be a 2x2 matrix for a spin 1/2, a 4x4 matrix for two spin 1/2 coupled, etc. And through mostly numerical diagonalization, we get the eigenvalues and eigenvectors of that matrix, which are the energies and the states. It tells us how these spins are mixed. So if we take, for example, this is the crystal field splitting caused by the electronic Hamiltonian, we have to add to the full electronic Hamiltonian this term that is called the Zeeman interaction, which is a magnetic field interaction with the electron spin and also with the orbital spin, because many times many electrons have an orbital angular momentum also. So this causes some splitting of the energy levels of basically all states or all orbitals of the molecule or the atom, but we only care about the ones that have unpaired spins. If these are all paired spins, it will not matter. There will not be any transitions there. So we only care maybe the top. So I didn't draw the electrons here, but you can think of copper 2, for example. So the spin Hamiltonian is much smaller than all these, but introduces all these effects up to this also as a basically semi-empirical parameters that are put in the spin Hamiltonian. So it's simpler, but it has, because it does not take into account all the interactions, it has to have some effective parameters, which can sometimes be calculated from theory using different theories like perturbation theory or more sophisticated methods. But if you do experiments, they are basically things that you fit to your experiment. So if we take, for example, the spin Hamiltonian of a simple, it's a one electron with an isotropic G value. Isotropic means the same in all directions. We write the spin Hamiltonian as this scalar product. That is, we saw that before. And then the scalar product is just the sum of the products of the components. So this would be the Sx operator times B0x, etc. But if we only have an isotropic spin, the G value can come outside of this sum, then we can choose always a coordinate system in which our Z axis, the Z spin, corresponds to the same direction as the magnetic field. So that's the same as setting B0x and B0y to 0. We are just changing our coordinate system, so we only get this term, which is non-zero. So the eigenvalues of this operator are plus or minus 1/2 times Planck's constant or something. So this is simpler than this. And then if we calculate for a spin 1/2, we take this Hamiltonian operator that we talked before, and we apply it to this plus 1/2 state, and everything is a number except for this operator. So this operator acts on the plus 1/2 spin state and gives us plus 1/2 again. So that's the effect. The h bar is not like it's put somewhere in between. We don't explicitly write it. The same for the minus 1/2 state. That would be the electron spin pointing down. In this case, would give us minus 1/2. And so the difference in energy between this one and this one, so these are the energies of each state. The difference energy, you can see it's the Bohr magneton times G. Okay, sorry. This is, I'm writing the same like in a more generic way. Just the energy of each ms is ms times this other number. So ms can be plus 1/2 or minus 1/2. So in the following one, if I take the difference, I think I skipped like I mixed two slides. But okay, if I take the difference from that, I get the energy difference is G times mu b times B0. So this gives me again the resonance condition that I mentioned before. So for measuring EPR, we use an EPR spectrometer. You have like 3 here. Usually the normal ones that work on X band is a range of frequencies, work at a fixed frequency around 9 gigahertz, and they sweep the magnetic field. So for more or less small fields, you can use like a normal conducting magnet that can be, for example, for the Bruker one, it's cooled with, so it's a tube of copper that has water running inside it. So it's cooled by water. But the small magnetic one, I think, has no cooling. So it has a smaller magnetic field range, but it has no cooling. For higher frequencies, I have seen that you can use hybrid superconducting and room temperature electromagnets. So those are superconducting magnets, but they can be swept, although more slowly. So that's if you go to frequencies that are 10 times higher, for example. So the more or less the way EPR spectrometer works is like there's a source, a microwave source. There's some microwave optical devices in between, and you go through what is called a waveguide. It's basically a tube. If you have seen the Bruker, everybody has seen the Bruker EPR here. So you can actually see the tube is rectangular. So that's basically the size, the dimensions of that tube are tuned to the wavelength of the microwave. So microwaves and any electromagnetic wave can travel through waveguides. These are basically tubes with conducting walls. So there's a waveguide here that goes into a cavity. The cavity also has dimensions that are tuned for that particular frequency. So if you want to change the frequency, you need to change the source, of course, the detector, everything, and the cavity. You need a different cavity for Q band, etc. So then you have an electromagnet, and you have a program of a source, a power source that controls the electromagnet. You have electronics that makes it very stable with very little drift, and you have a lot of other electronics, but that's basically the basics. So you put a sample and you sweep the magnetic field, and when you reach the resonance condition, there will be absorption of energy by the sample. So the returning wave will weaken, and there's a detector, a diode, that will sense like a fluctuation in the energy that is receiving, and that it will transform that into a signal. And then you have digital electronics that will digitize that signal and take it to the computer. So this is a similar EPR than the one that's here. It's just, this is the electromagnet. You can see the cavity, and here you can, behind this motor, there's a motor for tuning the cavity, but behind it you can see the waveguide, etc. Power source and stuff like that, console. These are this. Here you have the radiation source, but also the detector and a lot of the optics. I'm talking about microwave optics, you know, it's slightly different. So you have different frequencies. The most common one is X-band, around 9 to 10 gigahertz, corresponds to a wavelength of 3 centimeters, and for a G equal 2 species, you have a magnetic field of around 321 millitesla for 9 gigahertz. The magnet-edge ones usually are, depending on what you put in there, but usually around 9.45 or something gigahertz. Then you have Q band, W band. So here you start needing like a superconducting magnet, and beyond you need very strong magnets. So there are many experimental settings, and I cannot go through all of them, but one of the most important one is field modulation. So this will be an absorption signal. That's what initially it would detect if you don't have any field modulation. But while you're sweeping your external magnetic field, you put a small oscillating magnetic field that goes usually at 100 kilohertz. That is much a lower frequency than the actual frequency that you use to induce EPR transitions. So what it does is when you move the magnetic field, you are moving the signal. So when you have this modulation of the magnetic field at this point, your signal is proportional to the derivative of the actual absorption signal at that point. So if you increase your modulation, and you can change that from, I don't know, 0.01 millitesla to 1 millitesla in the magnet edge and 2 millitesla in the Bruker. If you increase your modulation, you increase your signal, okay? So because the signal is proportional to the slope of my absorption signal, what you are measuring in the equipment is the first derivative. So this is a way that has been designed, I don't know, probably decades ago, to really enhance the signal. So you can get much stronger signals through this magnetic field modulation. So the larger the modulation you set up in your equipment, the larger the signal is going to be, the less noisy. But there is, of course, always a catch, is that if you modulate with a larger amplitude than your signals, you start to distort them. So basically, so this would be an absorption spectrum. This is an example from EasySpin. There's a PDF there. So these lines have a full width at half maximum of 0.1 millitesla. So if you use half of that, 0.05 millitesla modulation, you will get this nice signal. But if you use a higher modulation than the actual line width, you see that, okay, this signal is going to be much stronger probably. These are normalized to 1, but you see that you start distorting it. And if, of course, you have a lot of details, you will lose them. Like you would completely erase all details that these lines could have. So you always need to play around with the modulation in order to find the optimal for your signal. This is another example. So this is a radical that has many lines, and then when you start increasing modulation, you really distort the lines, and eventually you get lower resolution. Okay? So sometimes you get lower resolution, sometimes you erase details, so you have to like test it for your system while measuring. Like, don't take only one spectrum, take several with different modulations to see what happens. So regarding the frequencies of the spectra of the EPR spectrometers, what they are good for is for separating G values. So they are not very good for separating. So the hyperfine splitting and other splittings that do not depend on the frequency directly. So it will not help you to go to a higher frequency for certain things, but you will separate G values. So this is, for example, a sample, I don't know, it's cobalt oxime. This is a cobalt, low spin cobalt complex. So this is what it looks like in X band, and in Q band you start separating the values, and D band, which is much higher, I don't remember how much, you really separate the different directions, different G values. But the hyperfine splittings are always the same. The problem is that if you look at the scales, these numbers are much larger. So the field swept is much larger in this case than in here. But the value, the separation between lines due to hyperfine splitting is the same. So these are other examples of the same. Like you can, okay, the same, actually, the same compound in different solvents. But basically you can use this for some things, but it's not a magic solution for everything to have a, higher frequency. Then, regarding the hyperfine interaction, there are three main causes of the hyperfine interaction. So that's the interaction between an electron and a nucleus. So you have the Fermi interaction or contact interaction. That is basically an interaction that arises from the electron being in direct contact touching the nucleus, because the nucleus takes up some space. It's not, it doesn't have zero width. So, and you have orbitals, like s orbitals, that have a non-zero probability of being in the exact position, the electron being in the nucleus. So when the wave function contains at zero is like the position of a nucleus, a notation for the position of a nucleus. When the wave function in the nucleus is not zero, then you have a contact interaction, and this always happens to some extent. So this is isotropic in principle. Then you have the magnetic dipolar interaction. So this is when you have like two magnets, you have an interaction between them that is given by this formula. This is like if they are tail to head, they attract. If they are head to head, they repel. If they have several different angles, they may attract or repel. That's a classical formula that has converted into its quantum mechanic counterpart. So you have all this stuff. This is the electron G value. This beta is what I call mu before. I forgot to change it. It's the Bohr magneton of the electron. But then you have the same, the nuclear magneton and the nuclear G values. So the nuclear G values are tabulated for different nuclei. And this is the electron spin and the nuclear spin operator. So this looks complicated, but it gives you a matrix basically. And then you have spin orbit coupling effects, which I'm not putting a formula there, but it's basically the interaction of the orbital angular momentum and the nuclear effect that also gets there, also is a part of the hyperfine splitting for certain types of systems. Usually not like CNO atoms, it usually doesn't matter, but if you have like copper or like transition metals or heavier atoms, it will matter, it will have some contribution, but it's not the main one usually. So if we take the simplest possible case, one spin 1/2 electron with one nucleus that has, in this case, has a nuclear spin of 1, so it has 3 different energy levels. So this is the Hamiltonian that gives what is called the Zeeman interaction. This is the interaction of the electron spin with the external magnetic field, and the hyperfine interaction. So this is a vector, this is a vector, this is a tensor. A tensor is basically a matrix. In this case, 3 by 3 matrix. So you can actually calculate this stuff is matrix vector products. If we take the simplest case and we say, okay, this is completely isotropic. So the G matrix is only G value, it's only one number for all directions, the same for A, then you can choose the same quantization direction for both matrices. So you can write like this, G, an isotropic G value times SZ operator, and then you have the SZ IZ operator. So this is the simplest possible case. And then if you calculate the energies for the different MS and MI states, so MI would be the magnetic moment projections of the nucleus, then you will have this formula. So this is MS, this will be plus minus 1/2 for one electron, this will be plus minus 1/2, and this can be for the case of let's say a nitrogen, 14 nitrogen, it will be plus 1, 0, or minus 1. So you can calculate the different energy levels. That's what is plotted there. And okay, I will give an example later with a spin 1/2, nuclear spin 1/2. But basically these are the energy levels as a function of the magnetic field. So the separations between them are given by the hyperfine interaction, but they don't depend on the magnetic field. And you only have transitions which are electronic. So you change the MS, but you don't change the MI. So that's an important condition. So these are different nuclei. So hydrogen, very important, like spin 1/2. Fluorine also can give a strong splitting. Phosphorus, copper, cobalt. You have two isotopes of copper, but they have very similar magnetic moments. So you can actually resolve lines due to this. Like for example, in copper porphyrins, you will have extra lines given by that ratio of the two isotopes. But in general, you will not see that. It will be hidden under the line width of the same with silver. You can resolve it sometimes because they are not exactly the same, but not always. So this is a case of a one spin, 1/2 electron spin and 1/2 nuclear spin. Could be hydrogen, could be fluorine, phosphorus. So these are the levels. I'm not going to go through all of them, but they're written here. You can later take a look at them. But basically, because you don't change the MI value when you do EPR transitions, you can subtract this energy with this energy and this one with this one. So that's the only two transitions that are allowed. So this gives you these expressions for the energies for each transition, and you can find the magnetic field for each of them, and you can do some more manipulation and basically solve this and find that the magnetic field splitting between the two lines is dependent on the A value, which is the hyperfine splitting, divided by the Born magnetomes times G. So this will change. So even if you have the same hyperfine splitting in different directions of your molecule, if you change the G value, the actual magnetic field splitting will change inversely. The higher the G value, the lower the splitting. That's not usually something that, unless you do very detailed analysis, you don't usually care about. Easy spin takes all of this into account. You don't need to, you just simulate. So the hyperfine interaction for simple isotropic cases is important for many organic radicals. So in an isotropic case, it's like when a molecule is moving around so fast that all the anisotropy gets averaged. So if you start with one possible transition in the absence of a nuclear spin, if you add one nucleus of 14 nitrogen, you split into 3. If you add a second one, you split each of these lines into 3. So I made the smaller segments, and you start adding them up, and then you get these 5 lines with this ratio of intensities. So for the interaction of one electron with two 14N nuclei, and you get like a simulation like this. If you add another 14N nuclei, then you further split each of the lines in 3, and you add them up, and you get this ratio, and this is more or less what it looks like. If you have 3 equal, these are equivalent 14N nuclei. Then, for example, this is a real case. I don't remember anymore which compound it was, but so this could be fit, you see, quite well with 3 14N nitrogens and 2 hydrogens with these values. So they are slightly different, but more or less 6 megahertz. And they are very similar to the hydrogen hyperfine splitting value. So that's a coincidence, but makes the spectrum look really regular and nice. When the spectrum looks very simple, that usually means that you have many interactions that have very similar values. If you start having, like if this is 6, but this is 9, you will have more lines. So it's like a coincidence that they like fall in the same place, more or less, the resonances. And okay, you could more or less do a diagram like this, but nobody does that. You just simulate. This is another real case. This is a collaboration. I forgot to put the reference here. There is some collaboration with Professor Jana. So there was this compound, and when we, I think, oxidized it, or I think they had isolated it. I don't remember if I did the electrolysis or it was already isolated. Yeah, maybe, yeah. So this is the pattern. So this is an experiment, and you see the simulation is quite good. We're probably not perfect, but quite good. And you can simulate it with all of these, and it was nice because it was very symmetric. So you can have these two nitrogens, you see them here, two hydrogens, you see them here with these values large, and these other, I think, two hydrogens with a lower hyperfine splitting. So in principle, you should start from the simplest case and start, if you cannot fit it with few nuclei that you know are in the molecule, you start increasing the number of nuclei that you add in the simulation. But always start from the simplest thing. And then, okay, this is an important topic if you do any transition metal, EPR, is G-factor anisotropy. So most interactions are anisotropic. So that means it has different values in different directions. The isotropic interactions are an exception, or are the result of fast motions in all directions of the molecule that average those anisotropic interactions. So the energy for different ms of an anisotropic system depends on a G value that depends on two angles that basically indicate the orientation in a spherical polar coordinate system. And this can be also represented with a matrix that contains, it's a 3×3 matrix that contains all these possible numbers, that some of them may be 0 or not. So that's a general case. Luckily, okay, before that, this means that you have a coordinate system x, y, z, and you have a G matrix that is defined by 3 vectors which are perpendicular to each other that point in some directions. And these have components. This will be gxx, xy, xz, zx, zy, zz, etc. You have different components. They don't have length 1, they can have different length, but they are orthogonal, okay, 90 degrees between each of them. So this is what you usually get when you measure single crystal EPR. Like, your experimental coordinate system may not match the particular coordinate system of the G matrices of the molecules. So you start from that. But usually you can find a coordinate system. So if I move the axis of my experimental system x, y, z to match the orientations of the G matrix vectors, then in that coordinate system your G matrix is diagonal. So you can always do that. You can always find a way to get from a full matrix to a diagonal matrix, which is of course much simpler. Then you get only 3 values and the others are 0. So I'm measuring this because that's what you see many times. It's something that you cannot avoid. I would like it to be more simpler, but it's not so simple. So from these values, you can calculate the G value in any orientation. So if you take these are spherical coordinates, it gives you an angle theta to the z axis and an angle phi of the projection of the vector in the xy plane to the x-axis. So maybe you have seen that somewhere, like in math. But so in spherical polar coordinates, you can find the G value for any angle using this formula starting from a matrix. So you can use this to fit single crystal EPR data. I don't think that any of you is going to do single crystal EPR. I did it my whole PhD, so it's like, yeah, I will never forget it. So, but why I'm measuring this? Let's say you have a powder. You don't have a single crystal, you have a powder that's like ground single crystals. You should always grind single crystals if you can. Like, don't use a powder directly from like a precipitation, because it may have some small crystals and not so small, and then it's not completely random. It's better to grind it before doing this. But the same will happen if you have a frozen solution. Then you have a lot of molecules. Each of them has a different G matrix oriented in a different random way. So they are, in principle, you have so many molecules that you are covering all possible orientations equally. So instead of, the way we solve this is assume the other way around. So a magnetic field here is in the z direction, and the molecules are oriented in all directions. So we can think of the problem in the other way around. we say, okay, we have one molecule oriented in one direction, but our external magnetic field will then be oriented in all directions equally. So it's a way of changing the perspective, of the problem. So then what we have is these blue things would be the G tensor of or G matrix of a molecule, and what we have is magnetic fields that are oriented in all directions. So like this, like this, like this. So what we see, if we sweep the magnetic field from the Z direction to the X direction, we assume that the GZ value is higher than the GX value. Remember, the scale is opposite, so higher G means lower B. So basically, while you sweep, you would see something like this. Of course, you see many more of these. So this is only 6 or 7 orientations, but you have infinite orientations, or almost infinite, or not infinite, but millions and millions of possible slightly different orientations. So you're sweeping something like this in this plane, ZX plane. Then you sweep in the XY plane, so you go from GX to some value GY. That's, let's say, in the middle. In this case, it's in the middle between GZ and GY. It's just, I'm talking about the value. So GZ could be 2.2, this could be 2.0, and GY, which I forgot to put the letter, could be 2.1, for example. So you sweep this is another plane. Then you sweep in the other plane, and you go here from GY here to GZ. So it's the same value, more or less. So when you do a powder spectrum, you're actually sweeping in all planes, not only these 3, but this is an example. So when you sweep all of them, you get contributions of all possible resonances for all possible orientations of the magnetic field to the total spectrum. So if you add up this plane plus this plane plus this plane plus all other planes, so these 3 are enough to tell you which are the values, but then you have all the other planes that are being summed. It's not that you sum them up. The experiment is summing them up because you have molecules in all orientations. So then if you can see that this value occurs here, all these values in between start to slightly cancel. The positive part of this resonance cancels with the negative part of the previous one. So you have 0 like here, and then okay, the same but opposite direction for the GX direction, and in between, because you have the GY value, it is repeated in several of the planes. This has a higher weight, and you see it more, much more intense than the other. So that's what is called a rhombic spectrum. So you have 3 different G values, and it looks more or less like this. It always looks like this, but maybe the X, Y, and Z labels that we put are written differently. But it can, of course, this can be closer to this side, this can be closer to that side. This would be a case for equally spaced G values. If you take a case where G, Y, and GX are the same, when you move in this plane, it's always the same, so you only see one resonance in this plane. So basically, if you add something like this, you would see this spectrum is called an axial spectrum. So this is much more intense than this part. And you have other cases, like an inverted axial would be if the larger, so if these values were larger than this one, you would see an inverted axial that would be, you flip it around, it's the same. So now some actual examples, because it was a little bit. So this is just an example. This again a paper from Jesse. I put this because it's one of my favorite papers that I was able to work in. So we did single crystal EPR. We did several stuff, and she did many more, and other people did more stuff. So this is like putting a crystal on the EPR, rotating it in 3 planes. So we use a cube that allowed us to move it in 3 orthogonal faces, so we can get 3 orthogonal planes. So this is low spin cobalt 2, and you see like an angular dependence. So that would be the formulas that I showed you for the G value with the cosines and sines squared. So it has this movement, and then you can fit it with some programs, or you can do it manually, and you get like an angular dependence of the resonances, and then you can use the center of the resonances to calculate the G squared values. So when you do this kind of experiment, you plot the G squared values for each plane, and you can use that to obtain a G matrix. And this would be the diagonal components of the G matrix, and you can find this orientation experimentally sometimes by analyzing the crystal morphology, but in our case we just did DFT and calculations, and because it was a square planar, very symmetric square planar complex, we already knew where it was oriented. So I should, okay, Toby, you for sure already heard all this, and maybe someone else also has, because I talk about this already like more than once. But okay, so that's an example, but you don't need to do single crystal EPR. Sorry. So I talked about G factor anisotropy, but I didn't say why. The reason for G factor anisotropy is the spin-orbit coupling. So everybody has seen spin-orbit coupling in some subject. Not everybody. Okay, just I'm going to skip a lot, but basically you have an electron going around a nucleus. When you have an electron moving, like moving charges generate magnetic fields. But because of relativity, I'm talking about Einstein's relativity theory, you can also think of this problem as the electron being stationary and the nucleus orbiting in the other direction, like this, around the electron. Okay, when you do that, the electron is sensing like a positive charge moving around that generates a magnetic field, and that is due to the orbital motion of the nucleus around the electron, which is the same but opposite to the orbital motion of the electron around the nucleus. So this makes an, let's call it nuclear magnetic field felt by the electron. So this, through some theory that I'm not going to discuss, tells you that there's some spin-orbit coupling interaction that's proportional to the, again, this is a simple energy of a dipole magnetic field, but this is the nuclear magnetic field, not an external one, and this is the electron magnetic moment. So you have these equations for a lot of things, and this is one possible expression, a simplified case for the hydrogenic atom. Like this effective magnetic field depends on the orbital angular momentum of the electron and all this stuff like the charge of the nucleus, etc., the inverse cube of the distance, but you put all this stuff into a parameter called, I think it's not zeta, it's, I don't remember the name of that Greek letter.
Xi.
Xi?
Xi.
Xi. Okay.
X.
Xi. So the spin-orbit coupling Hamiltonian is Xi times the scalar product of the orbital and spin the orbital and spin angular momentum of the electron. So that gives rise to a lot of stuff. One effect of the spin-orbit coupling is that you are starting to mix the different orbitals. I'm always talking about 3D orbitals because that's what I used more, but this applies to everything. So then you have this, the orbital angular momentum operators kind of mix these orbitals, the different ones. And these are possible couplings. So these mixings give a contribution and a net angular momentum of the net orbital angular momentum of the electron that will change where the resonance is. And then, okay, this I'm going to skip. The way to calculate how this affects the G values of the electron is through perturbation theory. But I'm going to skip all this because last time I think people were looking at me weirdly. But you can replace stuff and whatever. It's not that hard actually. And then you get to something like this. So this tells you that the P and Q would be X, Y, Z, P equal X, Y, Z, and Q equals X, Y, Z, so the different possible components of the G matrix. So delta G means the deviation from the G value of 2 is given by this summation, basically the different possible orbitals. Maybe this could be x squared minus y squared, and this could be xy, and how the different components of the orbital angular momentum couple those states. And this depends on the inverse on the inverse energy of those states. So you can simplify that a lot for a lot of cases. So you get, for example, for copper 2 that has a 1 ampere electron, you can have different possibilities. So you can have a elongated tetragonal distortion. You will have a ground state that has the ampere electron on the x squared minus y squared orbital. So that previous ugly looking equation can be simplified to this. So it's basically the G parallel value or G set value depends on the spin orbit coupling constant. Before was G, but now it's called lambda because there are reasons. And it depends on the splitting of the dx squared minus y squared and the xy orbitals. So you can actually calculate this. This gives you usually from 2.15 to 2.45. And this is usually another, like for other orientation, x and y, you get from, I don't know, 2.03 to 2.10. It depends how covalent are they. So if you have a ground state that's in the this set square orbital, that would be a compressed tetragonal, you will get these different equations for the G values. And if you have rhombic, you will have a mixture, and then you have 3 different G values, and you can more or less estimate the combination between the x squared minus y squared and the z square orbitals. You can more or less determine the weight from the actual G values. If you have, I don't know, low spin cobalt, you have okay, low spin cobalt would be similar to this, but not exactly the same. So you have the magic pentagon. So maybe you have seen this somewhere. Like it tells you the numbers that you put in here. If you couple xy and x squared minus y squared, you put here a minus 2i, and then here you can put also minus 2i for a certain value that would be, I don't know, the G z component, and then, yeah, this would be Lz couples this, Ly couples this, etc. So you can use that to remember all the terms that go into this perturbation expression. So you probably have seen this somewhere. And then these are, okay, now there are examples. So these are high spin cobalt complexes that I studied. So this is a G value of around GXY around 5. You see 8 lines because of the nuclear spin. And then here you see like a G set value around 2. And then, okay, there's another stuff regarding the dilution. There's an example of high spin iron 3. There's spin 5/2. So that's like high spin systems are even more complicated than low spin systems, but for some of them you have formulas for the G values. This is calculated through what is called rhombograms. And GXY is 6 and GZ is 2. And because there's no nuclear spin, you have one very sharp narrow resonance. So that's very nice for people who study high spin iron sometimes. You can get more complicated spectra also. Then this is another example. Again, this is a cobalt, low spin cobalt 2 porphyrin that it's actually low spin but has really big G values and really big hyperfine values. So you can get, these are the G values, for example, 3 point something, 1.8. And this is another porphyrin, but when you put an apical ligand, you change those energies between the dz squared orbital and the others, so you reduce the G values. So it has, if you can see like a similar shape, it's inverted axial, but then no hyperfine splitting in this line, but you see it here. The same way you saw it here. You only see 4 lines, but the others are hidden here. And you can even see like the splitting of a hyperfine splitting to the apical nitrogen. So that's very nice with cobalt porphyrins and stuff like that. Another sample, these are my own because it's easier to find my own figures than to search Google. But so these are cobalt and copper corrodes, which are cobalt or copper 3, but I can reduce them chemically. So if you reduce them, you see something like this. So this signal is some impurity, but you get something like this that is an inverted axial spectrum, and you can get the A values and the G values, 2.34, 2.28, and 2.00. So that means that the magnetic orbital is the dz square. And if you take a copper core, then the same you can see very similar with copper porphyrins, and you reduce it, this is with sodium borohydride, you get a copper 2 core that has a axial spectrum, or almost axial. So it has a lot of these, all these lines are super hyperfine splittings to the nitrogens. And these separations here are the hyperfine splittings to the copper nucleus. So you can actually fit all that and you will see, okay, the value is 2.03, 2.03, 2.12. You have a lot of covalency with porphyrins and corals and stuff like that, so you make the values closer to the G value of 2. Then another example, some other copper complexes, I think it's kind of like trigonal, and you can see, okay, the hyperfine splitting, and those are the parameters. And you also see the super hyperfine splitting, I think, of these 2 nitrogens. So 2 nitrogens will give you 5 lines. So I think you 1, 2, 3, 4, 5. Okay, maybe there are 7, but I think that's let me see. Oh, there are 9. Why? Maybe there's something else I'm missing there. But it doesn't matter. It probably comes from the nitrogens and something else. The backbone. Maybe. Maybe. I would have to read this. I will just put it as an example. But, okay. These are, I don't know, another vanadium examples. They have lines, but they are, so there's a huge table. I'm not going to go into details, but there's a lot of, like, if you have slightly different ligands on the vanadium, you will have different G values and A values, and you can get a lot of structural information out of those values for vanadium. For copper also, for cobalt also. Then you have what happens, like you have a nitroxide. There are many types of nitroxides that appear, but this happens to everything, but these are the best examples. It's an example of what you have in solution. So the previous things I mentioned were either powders or frozen solutions. So when you have, let's say, room temperature in a solution, you can have a rapid rotation of the molecules in all directions. So you average all anisotropy, and you see something like this. This is not perfectly isotropic, but it's close. This is called rapid movement regime. When you start to cool down, you start to have viscosity effects. So, or the same happens if you have big molecules. So if you try to measure a copper complex, even at room temperature, it will look like it's a slow motion regime, because the molecules tend to be large and the anisotropy is so large that it's not completely average unless you probably heat up a little bit. So that is slow movement regime that has like different like limiting cases. And when you freeze it, you go to the static regime that gives you, this is a rhombic spectrum, but this is tricky because that's not caused mainly by G factor rhombicity, but it's caused by A value rhombicity. So it's like the G values are not that different, but the A values are quite different because of the dipolar, magnetic dipolar interaction that gives rise to the anisotropic part of the hyperfine splitting is intrinsically anisotropic. So it has, like, let's say 10 megahertz in one direction and -5 and -5 on the others. So it's always there. You cannot avoid it. So when you freeze, you will see anisotropic hyperfine splittings. Then I wanted to mention, because, well, okay, everybody that does EPR here, or most do also EPR spectral electrochemistry. So you know the equipment, you know the cells. There are different designs of cells. This is like a sketch of maybe like similar to the last ones I had made that I have seen. They are mostly broken there. But what I want to say is, like, okay, you need to isolate the different electrodes. So sometimes you use like pre-coated wires, or you could use some separator, like, but it has to be very fine because everything has to fit in the tube. But the important thing that is, like, you have maybe a platinum working electrode. You have to increase its area so you can achieve electrolysis faster. And the reference electrode should be as close as possible. So it should be like, okay, isolated by next to the working electrode, not far away. And the counter electrode then should be relatively close, but you know, if this part of the tube is inside the cavity will be around 3 centimeters tall because of the wavelength of the X-band microwave. So let's say this is around 3 centimeters, then you have your counter electrode further away so that it will not contribute whatever happens in the counter electrode. It will not diffuse so fast, but it should not be very far away because you have a lot of resistance drop in there because you're using an organic solvent and you have a thin, long cell. So it's not a good, you know, not an optimal setup for electrolysis. So this should be very close and this should be not very far away, and it should be bigger than the working electrode, considerably bigger, at least twice the area. So this is an example. So this is what I was meant to see yesterday, but we didn't. So okay, again a corol, you can see the first and the second oxidation, and the third one you don't really, okay, more or less see it, but not really well defined. So the first one causes this radical signal centered on the corol here, the green one. Then when you start oxidizing more, you start reducing it, and then if you go higher in the potential to that third oxidation, this reduces even more and a different signal appears. So in an ideal setup, if you have a high concentration of your molecule and everything is, you know, you are lucky, you can actually see more or less the waves in the CV, in the EPR tube, and that can really tell you where where to do the electrolysis, and then you can actually see more than one oxidation state. You cannot always do that, but sometimes you're lucky. And this is after, like the blue one was the beginning, and then after I went to the oxidation, I went back to some value here, and then I reoxidized to around here, and I generated a signal. You see the red one that is slightly changed, and there's a new signal because there has been some degradation, but you can see that it is more or less reversible, the third oxidation. So you can go back more or less to the beginning, more or less, okay, because this is not CV. So you have diffusion, you are not electrolyzing the whole sample, so, but more or less. Sorry. Okay, this is shorter than the DFT one. So these are different examples, EPR parameters for copper 2, more or less what you would expect, G values, vanadium, cobalt 2. This is high spin, low spin. Of course, you have deviations from this, but these are more or less general values. Iron 3, if you have different spins like high, intermediate, low spin, you expect different things. And okay, these nitroxide radicals, also for organic radicals, usually very close to G equal 2, if it's all carbon, but then you usually have a lot of hyperfine splitting, so that's the interesting part to analyze. Then finally, simulation, because when you have many hyperfine splittings, the only way to obtain anything is through simulation, and if you want to publish, you usually need to simulate your spectra and provide the values. So you can use easy spin. For that you need MATLAB, but you have license here, or used to have, I think, also still have a license. Okay. So you can simulate a lot of stuff, a lot of any kind of EPR, pulse EPR, ENDOR, which is electronuclear double resonance, and many other things, magnetization, magnetic susceptibility, and you can fit. You can do a lot of stuff, super powerful. This is an example like a copper complex with 4 imidazoles. This is a spectrum. It looks similar to copper porphyrins, but it's not that apparently. So you can define a lot of parameters. I'm not going to go into this because anyone who tries to simulate will start from some program, from some previous program, from someone else, and they will ask like, okay, how do I do this? There's too many options. But you have to define the G values, the number of nuclei, the hyperfine values for all the nuclei, some experimental settings, and then option if you want some simulation options, and then you call Pepper, that would be for frozen solution or solid state, basically for static spectra, and you will simulate your spectrum. And yeah, that's it.